In this video, we're going to talk about PCBs and where they come from and what effect they're having on living things and living organisms and how they're affecting humans. Um, or potentially affecting humans in the future. So we're going to look at some of those items. So our PCBs are mostly found in every single thing that we use, almost every single everyday product that we're using. The big ones are going to be your electronics, and we find them a lot in electronic equipment. They're a liquid that they use in electronics, but they're also going to be found in a lot of different things. They're found in paint, clothes dyes, pesticides, and you have the whole list here. A lot of everyday products. And one of the big things that they do in humans, especially in adults, is that they disrupt liver function and disrupt liver metabolisms. They mess up with reproductive cycles. So we're going to look at how that all actually happens. The number one thing that they're known for is that they are what's known as hormone inhibitors and disruptors, or hormone mimics. So the way that works is that they mimic or prevent the release of the sex hormones, so estrogen and testosterone. And the biggest effect that we see from them right now, or that we can assess that the PCBs are doing, is we see a lot of what's known as intersex, like we saw in the video when they cut open the fish, and they had both the male and the female reproductive parts, the female and male sex organs, and that could create a hermaphroditic situation. It can also inhibit development. So we're going to look at how this all plays out. So in our normal cells, what we see is that the hormones would normally be produced, and what they do is they bind to a hormone receptor. And when they bind to a hormone receptor, it creates a cellular response, and that hormone is either made in the body, or it calls for some of that hormone to be made. So it triggers a desired response when the body needs certain things, like certain hormones. But what happens when you have one of these hormone mimics? So you have both mimics and disruptors. So we're going to look at the mimic. So some of these PCBs will act as a mimic, which basically mirror what the normal hormone looks like. So what they'll do is they'll bind to the hormone receptor, and when they bind to the hormone receptor, it elicits the same desired response. So like I have up here in the paragraph, says in cells affected by PCBs that act as hormone mimics, the PCBs are shaped and act exactly like the normal hormone. Therefore, they also find the appropriate hormone receptor and can produce an unwanted or an overenhanced cellular response. So if you have a hormone mimic that's in there that's mimicking something that maybe you don't really want inside the cell, what would happen is that hormone mimic would cause that cell almost like blindly disguise itself as something your body would need, bind with the hormone receptor, and then the cell would actually produce that hormone. Even though that hormone might not be wanted, it still creates that desired response. So it kind of is, a wolves in sheep clothing is really what it's about. Or it could be exactly like an already expressed hormone, and now it's going to overexpress that hormone, which is just as bad. The PCBs can also act as a hormone disruptor or an endocrine disruptor. So what happens in this case is that the hormone disruptor has the same connection pieces that the normal hormone has to the receptor. So in this case, it'll connect and it will create a response. So it'll either prevent the response from happening, or it'll create a different response that's not desired. So we see this a lot when we start talking about the hermaphroditic situations. We see this with the anti-estrogens and the anti-androgens. So what happens is it creates this androgynous hormone from binding, or blocks the androgynous hormone. So when the organism, as it's developing, the genetic code says, okay, the hormones for testosterone are going to produce because this is going to be a male organism, or estrogen is going to produce because it's a female organism. It creates these endogenous hormones that are released to prevent the other one from forming. So if it's going to be a male, it prevents the estrogen from forming. If it's going to be a female, it prevents the testosterone from forming. But what these PCBs do is that they disrupt the endocrine disruptor, disrupt that receptor. So the anti-estrogens cannot get through, or the anti-testosterone hormones cannot get through, and therefore they still are being able to be expressed in the organism. So it prevents them from actually stopping the other hormone from creating. So in our organisms that are adults, what we see this happening a lot in liver cells, and what it does is it prevents the liver cells from operating properly, and the liver cells help detoxify the body. So if they're not working properly, the body doesn't get detoxified right, and it can lead to a whole mess of problems messing with the metabolism and or leading up to different types of cancers. So we use in our PCBs, we use amphibians a lot to really tell us whether the PCBs are having some type of effect or could potentially have some type of effect on humans. And we do that for a couple reasons. One, like we talked about with the toxicity, is that frogs mostly get their interaction with toxic chemicals through dermal reactions. So the water is exchanging through their skin. So they're getting a high concentration of this toxic PCB or whatever, wherever it's coming from. The second reason we use them is because their endocrine system is very much like ours. So by monitoring their endocrine system, we can look at the frogs and we can say, oh, well, it's having this effect on their endocrine system if in greater concentrations, because obviously we are much larger than frogs, in greater concentrations, there could be a possibility that it could have the same effect on humans. And so the PCBs are something that we really need to worry about because they're increasing in the products that we're using, and we're seeing them more and more in waterways than we ever had in years. So I would say out of all the toxic chemicals that we're looking at, the ones currently that are most to worry about in humans would probably be these PCBs because one, we don't really know how they're going to react in humans, and if they're already inside of our bodies, we're pretty much the new generations that are going to see the effects of these PCBs. And two, we don't have a focal point into knowing as to when we look at that dose response curve where it's actually lethal, where it's actually going to be toxic, and ultimately what's going to be the big effect from these things. So those are things that we need to worry about when we're looking at them, and we use those indicator species to help guide us in our studies and guide us into how we monitor those PCBs and then ultimately how we're going to end up regulating them.